Hey, there you are. What is a line? You might recall your geometry teacher saying something along the lines of, it's a one-dimensional object with collinear points, it doesn't curve, and it has no endpoints. And that definition would be correct. But let's take a closer look at it. Specifically, collinear points. What is a collinear point? What is a point? In everyday language, we understand points to be tiny dots whose shape and size are so unfathomably small that they become meaningless. That's not too far off from the mathematical definition of a point. In 3D space, a point has no length, width, or height. It is dimensionless. That doesn't mean points are a useless concept. Not at all. In fact, the usefulness of a point comes not from the point itself, but from how it relates to its neighbors. Let's come back to collinear points. What makes 2 points collinear? We'll name 2 points Alice and Bob. Alice is sitting at the bottom of a hill. Bob has hiked ahead of her and is sitting on top. In Euclidean geometry, a line is simply the shortest distance between Alice and Bob. Any other path between the two would curve, and therefore would no longer qualify as a line. Alice and Bob are necessarily collinear because even if Alice decides she's had enough of Bob taking off ahead of her and blasts off in a spaceship to Mars, there will still be some shortest path between them. So far, so boring. But let's replace Alice at the bottom of the hill. Take a third point. We'll call him Max, and say he's standing on a tall rock, which puts him directly on the line between Alice and Bob. Now, the ratio of Bob's vertical height above Alice to his horizontal distance away from her is called the slope of the line between them. I know, we all remember what a slope is from school, but bear with me because things are about to get interesting. Because the line between Alice and Bob doesn't curve, its slope never changes. What this means is that, from Max's perspective, the slope of the line between him and Alice matches the slope of the line between him and Bob. The slope of the line at Max's position is therefore the same as the slope of the line at Alice's position and Bob's position. Here's the twist. Imagine that the rock Max is standing on disappears. Now, the slope of the line connecting Max and Alice is different from the slope connecting Max and Bob. Well, where does the derivative come in? Well, watch this. Max has a warp drive that allows him to move faster than light, and he's used it to bring his past self to the present 9 separate times. All 10 Maxes space themselves evenly up the hill. If we draw the shortest paths connecting each Max to his 2 adjacent points, we get something that resembles a curve tracing out the shape of the hill. Max didn't account for the fact that each of his past clones would catch up to his present self eventually, and now each clone has brought 9 more clones, who have spaced themselves evenly up the hill. This cycle repeats indefinitely, but Max, Alice, and Bob don't care too much because they have no dimension. They will always have a designated spot on the hill to themselves because they are infinitely small points. What happens when we try to draw a line between a Max point and one of his adjacent points? Well, it's not so easy to discern now. Whenever we try to find a point adjacent to one of the Maxes, a fresh Max clone pops up in between Max and the adjacent point. At some point, after desperately trying to connect the Maxes, we might step back and say, that's it. Instead of trying to connect 2 points at once, we should make a line that just touches one Max at a time. That line can only have one specific slope. If it tilts even slightly away from that given slope, the line will run into one of the infinitely many Maxes, or through Alice or Bob. Therefore, each infinitely small point on the curve of the hill must have an inherent slope value. Mathematicians call this special line, whose slope matches that of the point which it touches on the curve, a tangent line. The slope of the tangent line is what we call a derivative. Now, if you're just transitioning from pre-calculus to calculus, you may have learned the limit definition of the derivative. And it's a powerful mathematical tool, but it does not provide a great insight into what's going on. Take a look at this notation. D over dx of y. Seems opaque and out of left field, doesn't it? Let's label the plane in which the 2D hill sits. The horizontal axis is the independent variable x. The vertical axis y is a function of x. The y function takes in a horizontal distance and spits out a vertical height. X is the variable you can, well, vary the value of. In the hill analogy, Max can walk horizontally on the hill, but Max can't levitate vertically into the air and directly change his y value. Max is constrained to walking forward or backward on the surface of the hill, and his elevation above the base of the hill changes depending on where he is along the x-axis. D over dx of y is really saying, hey, find an equation of the tangent line for y of x, and write that equation in terms of the variable x. Because the tangent line isn't allowed to run into any of the other points on the function's curve, that says a lot about the shape of the function on either side of the point which we've taken the tangent line of. If the tangent line is steep, the curve immediately adjacent to a point must be steep as well. If it is flat, the curve must be mostly flat as well. This flatness of a function is what we call a rate of change. Back on the hill, Alice and Bob want to know what their tangent lines are. She's sitting at the very base of the hill, where the ground first becomes flat, and he's at the very tip top, where the ground is also flat for a very brief moment. Both their tangent lines are therefore flat. The rate at which the elevation of the ground they are positioned on changes is 0. Let me rephrase that, say that again. At the exact spots where Bob and Alice are sitting, the elevation of the ground is neither rising nor falling. The ground is flat. Now, look at Max. He's on a part of the hill that has a steep slope. The elevation of the clone in front of and behind him is different from his own. You can see that the rate of change of the hill's elevation at his position is large. He knows from his tangent line that the hill isn't flat where he's standing. Derivatives are a beautifully logical abstraction of slope applied to infinitely small chunks of a curve. In a nutshell, they tell us how flat or steep a curve is at a chosen point. Their fundamental simplicity is unassuming, but they are foundational tools to an astounding breadth of fields, from population dynamics to economics to mechanical engineering and quantum mechanics. Derivatives are everywhere. Who knew that lines could be so useful? As always, thank you for asking.